Okay, it's time. Okay, so let's get started. Good morning, everyone. My name is He Qian. I'm from Material Science Department. Today is my great pleasure to introduce my colleague, Prof. Mao Xianwen, as today's seminar speaker. So I will first give you a short introduction of Prof. Mao Xianwen, who recently joined us as assistant professor in the Material Science Department, and he is also the awardee of the Presidential Young Professorship, yes, which is highly competitive. He obtained a bachelor's degree in polymer materials and engineering from Tsinghua University, which I think is still belongs to the chemical engineering department, right? And a PhD in chemical engineering from MIT. Doing his PhD, Xianwen also worked as several internships, including industry in Italy and National Renewable Energy Laboratory in the US. His work focused on molecular engineering and soft materials with tunable, catalytic, and absorptive properties for sustainability. He did his postdoc in Cornell University, over there he worked on developing single molecule particle techniques for operando functional imaging of complex energy materials. I work on electron microscopy. We more focus on structures, but we never be able to see functions. So Xianwen's expertise is really unique here. He has numerous awards, and he has filed 7 patents and many media coverage. So without further ado, let's hear what he has to say today.
Yeah, cool. Thank you, Qian, for the very kind introduction. Today, I will be sharing with you some of my research on understanding electrochemical interfaces for developing sustainability technologies. I'll focus on insights from soft material design and operando functional imaging. So now you may already start to wonder, what are these data? So these are actually stock price or market value of Tesla and Toyota. Last year, Tesla has overtaken Toyota to become the world's largest car maker in terms of the market value. But Toyota actually makes 300 times more cars than Tesla. So why investors' confidence in Tesla? Is it because they really like this guy, who apparently needs no introduction? Or more likely, they really liked his vision about clean energy technologies. So I'm not trying to sell you the Tesla stock. I checked the recent trend is still going strong, but the stock price really aggregates different pieces of information. So it reflects the investors' expectation about the future. Clean energy is the future. 2020 has been the warmest year on record. Decarbonization has never been more urgent. Many countries, including the US and China, have announced ambitious plans to combat climate change. So there are tremendous economic opportunities for clean energy technologies. In many emerging clean energy technologies, electrochemical systems are the key components. A report from NREL identified a promising pathway to a low carbon future is through growth decarbonization coupled with electrification. So the key challenge here is deep electrification of many processes in many sectors that are traditionally thermochemical. So effective electrification requires highly effective electrochemical systems, for example, electrochemical flow system for wastewater treatment, or electrochemical water splitting system to produce carbon-free green hydrogen. So the key challenge here is to lower the cost and improve efficiency in electrochemical systems. And doing so requires a fundamental understanding of very complex electrochemical interfaces. For example, how the transport and kinetic processes occur and how they interact with each other, all together govern the overall performance of the electrochemical systems. So my research has been focused on understanding electrochemical interfaces by elucidating the fundamental processes that occur at such interfaces. For example, ion packing, electronic transport, and interfacial catalysis. I have two primary research thrusts. The first one is focused on design of electrochemical active soft materials. And the second one is focused on using single entity functional imaging tools to study photoelectrochemical materials. And today I'll be sharing with you a couple stories. And now I'll get started with the first one, which is about understanding how self-assembled nanostructures in electroactive ionic liquids can facilitate charge storage or energy storage at electrified interfaces. Ionic liquids are very promising electrolyte systems for energy storage because of their low volatility, non-flammability, and electrochemical stability. So they are particularly suitable for large-scale applications. However, ionic liquids show very complex ion ordering on electrode surface. So they often display very elusive, very difficult to understand electric double layer structure. So understanding the fundamental electrochemistry of ionic liquids has been an active area of debate. Most previous research focused on non-amphiphilic ionic liquids that do not show self-assembly behavior. And our work focused on surface active ionic liquids that contain amphiphilic structure, for example, shown here in this ALT anion, a polar head and a non-polar tail. And this amphiphilic structure will lead to the formation of self-assembled nanostructures due to the strong hydrophobic interactions between the non-polar tail. And they can form the self-assembled nanostructures in the bulk of the liquid, as well as on the electric surface. The prototype amphiphilic ionic liquid we study is this beaming ALT. So it contains a large anion ALT, again, a polar head, a non-polar tail, so it's amphiphilic. As a control system, we also studied another non-amphiphilic ionic liquid that shares the same cation, but a very different anion, BF4. So BF4 is a very small anion, it's not amphiphilic. From neutron scattering measurements, we found the amphiphilic ionic liquid show a strong peak, which indicates the presence of self-assembled nanostructures in the ionic liquid. And the location of the peak corresponds to a characteristic length of 22 angstroms, which quantifies the size of the nonpolar domain and is consistent with the length of two nonpolar tail from ALT. And by contrast, the non-amphiphilic ionic liquid doesn't show such a peak, which indicates there's absence of such self-assembled nanostructures, which is expected. Now we move on to perform electrochemical measurement to measure their energy storage performance. So we measured their specific capacitance as a function of scan rate, and the capacitance is an indicator of their energy storage performance. At a low temperature, 25 C, the amphiphilic ionic liquid shows much lower capacitance than the non-amphiphilic one. And that is because the amphiphilic ionic liquid is highly viscous at a low temperature. And the larger viscosity usually leads to a smaller capacitance. And what is more interesting to us is at this high temperature, 200 C, where the viscosities of the two ionic liquids are essentially the same. The amphiphilic ionic liquid shows much higher capacitance than the non-amphiphilic one. So here the viscosity doesn't play a role. Essentially, we think the difference in energy storage performance should be due to the difference in their molecular structure. So to understand the difference, we compared in detail the electric double layer structure between the two types of ionic liquids by molecular dynamics simulation. First, we look at the non-amphiphilic one, which shows this typical charge alternating structure. So cation, anion, this is number density of the anions and cations. It can show the structure on the surface persists for about 8 ion layers. By contrast, the amphiphilic ionic liquid shows a very different, very unusual electric double layer structure. you can see a very strong first peak and decays very quickly. And we think this is because the formation of the nonpolar domain along the electric surface that squeeze excess cation into the first ion layer. So a very strong first peak and decays very quickly. Now, all the ion ordering behavior revealed by molecular dynamic simulation were further experimentally verified by AFM measurements. So essentially, we do AFM force measurements, and in those measurements, we use an AFM tip to push through the liquid and to measure the location of rupture force, 1, 2, 3, 4. And you can see that the location of the rupture force is really consistent with the locations revealed by simulation, location 1, 2, 3, 4. And that is also the case for the amphiphilic ionic liquid, location 1, 2, and location 1, 2. And importantly, the interstep distance are very different in the two ionic liquids. So for the non-amphiphilic one, the interstep distance is about 5 angstroms, which is consistent with the size of ion pair. And for the amphiphilic one, the interstep distance is much bigger. It's about 22 angstroms. And it's really consistent with the size of the nonpolar domain. So these results really indicate the AFM force measurements can capture the difference in electric double layer structure experimentally between the two different kinds of ionic liquids. So by now, I hope I have convinced you the amphiphilic ionic liquid shows a very unusual, very different electric double layer structure compared to typical smaller size ionic liquid, non-amphiphilic one. Now the next question is, how does this unusual electric double layer structure translate into enhanced energy storage performance for the amphiphilic ionic liquid? To answer that question, we calculated the differential capacitances for the two ionic liquids as a function of applied potential or electropolarization degrees. For the non-amphiphilic one, it shows a typical U shape, and which is consistent with literature, and is typical for smaller electrolytes. What is interesting to us is the relative performance between the two different kinds of ionic liquids. At a low polarization degree, the amphiphilic ionic liquid shows lower capacitance due to the accumulation of neutral tails on the electrode surface. So at low electropolarization degree, the electrode surface is uncharged. So it interacts very strongly with the nonpolar tail of the ALT anion. So therefore leads to accumulation of neutral tails on electrode surface. And this can be verified by MD simulation as well. So here is a number density of the carbon atom at the end of the nonpolar tail. And you can see that at a lower electropolarization degree, the number density is much higher compared to the case with high polarization degree. So this really confirmed the accumulation of neutral tails on the electrode surface at a low electropolarization degree. At a high electropolarization degree, we observe that the capacitances of two ionic liquids decreases with increasing polarization. So these trends are observed in many electrolyte systems, essentially due to the lattice saturation effect resulting from the steric constraints of ions. But what is more interesting to us is at this intermediate polarization degree, we observe a much higher capacitance for the amphiphilic one. And we think that's due to the presence of the nonpolar domains that suppresses over-screening effects, effectively leading to a thinner electric double layer and therefore larger interfacial capacitance. So it's very different for the non-amphiphilic one. And you can see they often show this typical charge alternating structure leading to over-screening. So a very thick electric double layer and a very small interfacial capacitance. So these trends were previously reviewed by simulation results, and we confirmed by experiment. Essentially, we performed electrochemical impedance spectroscopy to measure the differential capacitances experimentally for the two ionic liquids as a function of applied potential at 3 different temperatures. Although the fine features such as the location of the local minimum and local maximum differ between simulation and experiment, but the overall trends are quite consistent between simulation and experiment. All the data I showed before are for just one type of amphiphilic ionic liquid, beaming ALT. So to test whether in general, amphiphilic ionic liquids can outperform non-amphiphilic ionic liquid in terms of their energy storage performance, we tested other surfactant ionic liquids using different kinds of surfactant long chain anions. And they are different than ALT. So the general consensus is that at intermediate electroporation degree, amphiphilic ionic liquids generally outperform non-amphiphilic one. And this work on amphiphilic ionic liquid is a truly collaborative effort from an international team of scientists with very different skill sets, ranging from synthesis to MD simulation to different kinds of material characterizations. But this work is not just a result of diversity in expertise. We are a very socially diverse group. So when we work together, we anticipate different viewpoints and we work harder to reach consensus. Study shows diverse teams produce higher quality papers or more citations. I hope that's going to be the case for our paper as well. So I feel fortunate to be in the MSc department where we have very diverse faculties and we are doing highly interdisciplinary research. So I'll continue to pursue collaboration opportunities to work with scientifically and socially diverse groups and teams. And now I'm gonna switch gears to discuss some of the work from my second research thrust, which is on single entity functional imaging. So I think single entity studies provide complementary information to typical bulk level ensemble averaged measurements. So here, single entity imaging will allow me to probe, to measure the properties or functions of materials at the single entity level, such as single particles shown here, or single interfaces, or even single polymers. So providing unique insights inaccessible from bulk level ensemble averaged measurements. And here I will share 2 stories with you. I'll get started with the first one, which is on how to use functional imaging to guide material design for water decontamination applications. Essentially, we do single entity functional imaging. So why is this important? Why do we care? Let me give you one example about catalyst design. The key to rational design of catalysts relies on a clear structure-function relationship. Using bulk materials, however, sometimes it's quite challenging to establish a very clear structure-function relationship. The bulk material often contain many catalyst particles with different sizes and shapes. And different size and shape is often associated with different catalytic activities or functions. And here in single particle imaging, I can measure a single particle in terms of its structure as well as its function. So I can establish an ideal one-on-one correlation between the structure and the function of exactly the same catalyst particle. And single particle imaging can also allow me to obtain sub-particle level information. For example, where this reaction occurs is on this facet or different facets or at the corner. Essentially, the foundational technique we use is super resolution reaction imaging. And now let me play a movie for you to illustrate the working principle of super resolution reaction imaging. Just ignore the bird chirping. I don't know if you can see there's like actually fireflies in the movie blinking on and off. So this is not experimental data. It's not a movie I took in the lab, but right outside my apartment at Cornell. So essentially, super resolution reaction imaging is based on single molecule fluorescence microscopy. And in this microscopy, you produce single fluorescent molecules one at a time in a diffraction limited region. And these single fluorescent molecules are just like fireflies, blinking on and off. So they are not turned on at the same time. So they don't overlap. Because they don't overlap, you can super localize them to a spatial resolution about 10 nanometers, which is much higher than, is significantly improved than the typical spatial resolution about 300 nanometers observed in conventional optical microscopy. And single molecule fluorescence microscopy has been typically used for structural imaging of biological systems. And the photo switching and the photo activation are the primary mechanisms to produce single fluorescent molecules. And here, in super resolution reaction imaging, we rely on different mechanisms to produce single fluorescent molecules. Essentially, we depend on surface fluorogenic reactions on catalyst particles to produce single fluorescent molecule, one at a time, in a diffraction limited region. So super resolution reaction imaging, similar to other super resolution techniques, can achieve a spatial resolution about 10 nanometers. So it is very suitable for studying nanoscale catalyst particles. It has become a powerful tool to study nanoscale catalyst particles because it can address three primary challenges associated with characterization of nanoparticles. So there is always interparticle heterogeneity. Now I show two different kinds or two different nanorods. And these are their representative super resolution images. And here a brighter color indicates a higher catalytic activity. Now you can clearly see, even though the two rods look similar, but their catalytic activities are quite different. For the first one, you can observe two catalytically hot spots. But for the second one, there's a more uniform spatial distribution in terms of their catalytic activities. And sometimes, even within the same catalyst particle, the catalytic activities is different. For example, within the same gold nanorod, the catalytic activity is higher at the center. And for the zeolite crystal, the catalytic activity is higher at the edge. And sometimes, catalyst particles can even show dynamic disorder, meaning that their catalytic activities are different at different times. So here I show 5 images for the same catalyst particle, but obtained at different times. And you can see that the catalytic activities are very different at different times, and the spatial patterns are quite different as well. Essentially, super resolution reaction imaging would allow me to follow reactions in real time with a nanometer spatial resolution. So it's very useful to study nanoscale catalyst particles. However, there is a primary limitation in super resolution reaction imaging. So essentially, it can only study fluorogenic reactions. Super resolution reaction imaging is a fluorescence microscopy-based technique. So apparently, it can only study something that fluoresces. But only a very limited number of reactions are fluorogenic, and most of them are summarized here. Many very important reactions are completely non-fluorescent. So even though it's a powerful tool to study nanocatalytic particle, super resolution imaging has very limited applicability. It is only limited to study fluorogenic reactions. To overcome this long-standing challenge, I developed an imaging technique called COMPETES that enables super resolution imaging of non-fluorescent reactions. So COMPETES stands for Competition-Enabled Imaging Technique with Super Resolution. In this technique, we essentially use competitive chemistry as a strategy to interrogate completely non-fluorescent reaction. The basic idea is quite simple. Essentially, you have two different kinds of reactions. One is non-fluorescent, which is your target reaction. But there's another one, it's an auxiliary reaction, but it has to be fluorogenic. Now, if the two reactions compete with each other for the same surface site, as shown here, the introduction of the non-fluorescent reaction will lead to a suppression of the fluorescent signal from the auxiliary fluorogenic reaction. And this degree of suppression can be imaged at the same super resolution as a fluorogenic reaction. So this can provide super resolution spatial information of the completely non-fluorescent reaction. So the key idea is like this. You have a reaction you want to image, but you need to find another auxiliary fluorogenic reaction that competes with it. And I demonstrated the utility of the competes imaging technique by studying a photoelectrochemical reaction. And here is the imaging setup. I have two lasers, 405 and 532. The 405 laser is to generate charge carriers within the catalyst particle. And the 532 is to induce a fluorescence from the product molecule from the fluorogenic reaction. And more specifically, my target non-fluorescent reaction is hydroquinone oxidation. So hydroquinone is a primary water pollutant. So this reaction is important for water decontamination. The auxiliary fluorogenic reaction is amplex red oxidation, which produces a highly fluorescent molecule resolution. And the catalyst we studied is bismuth vanadate, which is an important material for a range of energy and environmental applications. Now, as I alluded earlier, in order to do competes imaging, first, you need to establish there's indeed competition between the two reactions. To do that, we performed ensemble level measurements. So we measured the fluorogenic reaction rate as a function of competitor concentration. And we also measured the target non-fluorescent reaction rate at the same condition. And you can see that the auxiliary fluorogenic reaction rate decreases with increasing competitor concentration, while at the same time, the non-fluorescent reaction rate increases. So essentially, these trends indicates the competitive behavior, really confirming there's competition between the two reactions. So now I can move on to do competes imaging. A competes image is obtained by first obtaining two typical super resolution reaction images for the auxiliary fluorogenic reaction without and with competition. So here are super resolution reaction images. A brighter color indicates a higher catalytic activity for the auxiliary reaction. And you can see with the introduction of competitor hydroquinone, the fluorescent signal is suppressed. And this indicates, again, there's competition between the two reactions. And the white lines are structural contours for the same catalyst particle obtained by its SEM image. So essentially, we do correlated measurements. We measure the function of single particle under optical microscopy, and we transfer the entire sample to either SEM or TEM. So we can do correlated measurements to establish structure-function relationship. Now a competes image is obtained by doing the inverse difference between the two images without competition and with competition. So there's nothing fancy here. Images are just pixels with numbers. You can do all kinds of mathematical manipulation. You can do, you can add them together, you can subtract. But here I chose to do inverse difference because this inverse difference is physically meaningful. It reflects the magnitude of hydroquinone binding affinity. So in the competes image, a brighter color indicates a stronger or higher hydroquinone binding affinity. And you can see that from this image directly that the basal facet of the hydroquinone binds more strongly on the basal facet, it's brighter color here, than on the lateral facet, there's darker color here. So now I quantify the hydroquinone binding affinity by just using two different concentrations. In order to have an accurate quantification of the binding affinity, you need to do a systematic concentration titration. Essentially, you just measure the same particle under different conditions. So these 5 images are for the same catalyst particle, but are measured at different competitor concentration. And you can immediately see that a higher competitor concentration leads to a more significant suppression of the fluorescence signal. And again, this indicates competition. And because competes is really an imaging technique, it provides spatial information. It can provide subparticle level information. So from this image, I can do subparticle level, facet-specific hydroquinone titration. How can I do this? It's actually quite simple. Essentially, just look at the image and collect all the events just from the basal facet. Then you can produce a titration curve just for the basal facet. And you can do the same thing for the lateral facet. And now I plot the inverse rate as a function of hydroquinone binding, hydroquinone concentration, because the slope here directly reflects the magnitude of hydroquinone binding affinity. And you can directly see from the two curves. The hydroquinone binds more strongly on the basal facet than on the lateral facet. And this is consistent with the competes image I just showed earlier. So now you may wonder, you took all these efforts to produce these beautiful images. So why do I care as a material scientist? What kind of design principles, useful guidelines we can obtain? Essentially, here are the results I showed just for one particle. If I do this for many, many particles with different size and shapes, and look at that one at a time, pull the results together, this quantitative imaging results will allow me to distill particle morphology design principles to optimize water decontamination efficiency. The catalyst particle we study here is bismuth vanadate with a well-defined morphology. So it can be described by a size parameter L and a shape parameter psi, S over L. So the size parameter is quite easy to understand. A bigger L just indicates, excuse me, a larger particle. And the shape parameter psi, when it transitions from 0 to 1, essentially this indicates the morphology of the particle transitioning from this bipyramid to truncated bipyramid to a plate-like morphology. So all these quantitative imaging results I showed earlier would allow me to predict an important parameter omega, which is overall pollutant removal efficiency per unit mass. And I can predict this parameter as a function of particle size, as well as a function of particle shape. So here are the heat plot for the overall efficiency parameter. A brighter color indicates a larger overall efficiency. The shaded surface is the prediction. The circles are experimental data, and they agree with each other. Now, if you project the 2D plot onto the x-axis, you can immediately see that the overall efficiency parameter decreases with the increase in particle size. This is easy to understand because a smaller particle has a larger surface to volume ratio, so therefore has a better decontamination efficiency. Now, if you project the 2D plot onto the y-axis, and you can study the shape dependencies. At different size regimes, you can see the shape dependence are quite different. sometimes monotonically increasing, sometimes monotonically decreasing. What is interesting to us is at this intermediate size regime, it shows us very interesting biphasic behavior. So this indicates if you have an intermediate sized particle, in order to improve water decontamination efficiency, you want either this morphology or that, never somewhere in between. So these water decontamination particle design principles were previously unknown because they are for a completely non-fluorescent molecule, non-fluorescent reaction. So they are made possible by the complete imaging technique I developed. Now I'm gonna switch gears to discuss the second story, which is how to use functional imaging to guide material design for water splitting applications to produce carbon-free clean hydrogen. Photoelectrochemical energy conversion is a very important technology to produce clean fuels, including hydrogen. So this technique has been developed a long time ago. Now the challenge is to lower the cost and improve efficiency, improve the performance. In order to do this, the key challenge is to improve the performance of photoelectrodes, especially photoanode, because of the very sluggish, very complex, multi-step water oxidation kinetics on the photoanode. So my focus is to establish photoelectrode design principles by using insights from functional imaging. Functional evaluation of photoelectrochemical materials or photoelectrode materials have been done at different structural levels, ranging from ensemble level, where you can make a bulk film and measure the typical performance metrics, or at a single particle level. For example, here you can make a micro-patented electrode and measure the photocurrent or performance of just a single silicon nanowire, or even at the subparticle level. So here, a recent report shows the measurement of local photocurrents on a single faceted semiconductor nanorod. So they can measure photocurrents on the same facet at different locations and compare what is going to be the interesting behavior if you measure just different sub-facet level locations. But this is a single faceted semiconductor photoelectrode. I am interested in more complex, multifaceted semiconductor materials, for example, bismuth vanadate, strontium titanate. So essentially, these multifaceted semiconductor particles will have better performance or expect to have better performance and photoelectrochemical properties, essentially because the work function difference among different facets can facilitate preferential charge accumulation onto different facets. Essentially, this is due to the energy level difference between the different facets. So when you shine the light onto this anisotropically multifaceted particles, the electron holes sometimes go to different facets. And this preferential charge accumulation onto different facets can help suppress surface electron hole recombination, therefore improving the performance of the photoelectrochemical materials. However, all the previous studies only focus on the difference among different facets. They didn't consider the intra-facet variation of local electronic properties. So they did not consider within the same facet, is there any difference in terms of the electronic properties? For example, in this shaped bismuth vanadate particle, a previous report shows that at different facets, they have different energy. But they never consider the intra-facet variation of local electronic properties. So here, we hypothesized, because the different facets have different energy levels, when they meet, they form this interfacet junction, which essentially leads to intrafacet variation of local electronic properties. And now, if you put the catalyst particle, an isotropically shaped catalyst particle in an electrolyte solution to perform, for example, photoelectrochemical water splitting, you'd expect to see that at different subfacet location, the band bending degrees will be different. So the local photocurrent, even within the same facet, would expect to be different. Now, to test those hypotheses, we developed multimodal functional imaging to evaluate photoelectrochemical particles. In the mode 1, we essentially can measure the subfacet level photoelectrochemical currents by using a focused laser beam to scan across different subfacet locations across a single particle. And we can also use wide field imaging to map the surface electron hole activities by using hole probing, electron probing, fluorogenic reactions. So this essentially would allow me to look at where will be the high hole and high electron activity sites on a single particle at nanometer spatial resolution. And then we can also perform whole particle photoelectron measurements. And this is the ultimate metric to quantify what kind of particles with what size, with what shape can produce the overall, can deliver the overall best performance in terms of the photoelectrochemical current. Essentially, we developed this multimodal functional imaging to do everything together on the same catalyst particle. And indeed, we found there's intrafacet variation of surface hole activities and the surface electron activities, as well as local photocurrents. So these surface hole, surface electron activity results, combined with local photocurrent mapping, will allow me to obtain information about local flat band potential and electron hole separation efficiencies. Essentially, from this plot, you can see that there's clear intrafacet variation of local electronic properties, such as flat band potential. At different subfacet location, the flat band potential is different, which is essentially already manifested in the local photocurrent variation. Now, the important thing is the S-like spatial profile of flat band potential is really consistent with our earlier hypothesis. So this really confirming the existence of interfacet junction effect. So all the work I discussed today are from my efforts during my PhD and postdoc. So I'd like to acknowledge my PhD advisor, Alan and Greg, for their support, and my postdoc advisor at Cornell, Penn, for his support as well. And I'd like to thank many, many collaborators for all the work. And finally, but not the least, I'd like to acknowledge various funding agencies for the financial support. And thank you so much for listening to my talk. I will be happy to take any questions that you may have. Thank you so much.
Okay, thank you, Xianwen, for the exciting talk. It's definitely an eye-opening experience for me. Audience, if audience have questions, you can raise hand or just type it in the chat. I don't see any coming up at the moment. If you raise hand, we can unmute you so you can speak directly. While waiting for the audience to ask questions, maybe I'll kick off with a couple of questions for my own. Okay, so as my cross-piece, I think it's very natural for me to ask, for your functional imaging, for your super resolution imaging, what is your time resolution and spatial resolution?
So the spatial resolution is typically from 10 nanometers to 40 nanometers. It depends on the signal to noise ratio. So in our photoelectrochemical catalyst study, it's typically 30 to 40 nanometer spatial resolution. But for cleaner measurements, like gold nanoparticles, without all this complication from like photo excitation, it can be 5 to 10 nanometers. So it's like super resolution technique. It's typically within 5 to 10, but sometimes because the reaction is really complex, we can only do like 40. And in terms of the temporal resolution, it's quite slow. So it's not really high because you sacrifice the time in order to obtain the spatial resolution. Essentially, we have to separate the generation of fluorescent molecules over different times. So the temporal resolution is about 10 milliseconds. So I think if you study something that has activity change, like surface restructuring within like a minute, certainly you can do that, but it's not in the ultra fast region at all. It's like 10 milliseconds-ish, the temporal resolution.
Okay, thank you. I see Stefan has a question. Stefan, you can unmute. And then I see Prof. Chen also has a question. So,
simple question. A usual issue with the ionic liquids tends to be their viscosity. I also saw your measurements were mostly at elevated temperatures. What is the rate capability of this ordering processes at the room temperature?
Yeah, so if you just compare the power performance, it's really low if we use amphiphilic ionic liquid. But at higher temperature, when they are less viscous, they are like better in terms of both energy density and the power densities. But we try to solve that problem by mixing different types of ionic liquids together. So essentially what we will try to utilize is an amphiphilic structure that leads to unique surface electric double layer structure from the amphiphilic structure, right? So if you mix a non-amphiphilic one with amphiphilic one at an optimal composition, you can still achieve better power performance at a room temperature. We showed some of those data, showed some promising results. We don't need the entire liquid to be the amphiphilic one. We need a little bit, like 25% of it to be the amphiphilic one. So at a room temperature, by using the mixture, we can have both better energy density and the power performance as well.
Okay, thanks.
Yeah, thank you. I think Prof. Chen.
So I have a question. I'm not a chemical guy, so but I'm frequently use the ionic liquid to modulate some physical properties in some oxide, okay, in our spintronics materials. So I have one question. What the difference between the iron liquid you use in the compared to commercialized iron liquid, you know?
Yeah, so essentially the commercial one has much smaller structure. So it doesn't form this ordered structure along the surface. So what I have is bigger anion. So they have hydrophobic tail. They interact with each other.
Yeah.
They form this laminar structure, so ordered nanostructures. That's something unique about the ionic liquid I was talking about. So typical, if you buy off the shelf, the commercial one, they have smaller structure. They have like maybe 4 carbons, but what I have like 20 carbons. So 4 carbons usually don't give you the self-assembly behavior. So the typical one behaves more like a smaller, typical inorganic electrolyte in terms of the electric double layer structure. It's more like sodium chloride, but you use it for other purposes in your application because it's non-volatile and it's like green solvent, right? So we have a different electrochemical properties if we use the amphiphilic one we have.
Okay, thank you. Yeah. So in that case, people now use the iron liquid to modulate the physical properties of some materials, just using the, the electric field effect, right? It's not like using, the chemical reaction between the iron liquid and, but for this one, if you use the self-sampled, so the electric field is still maybe it's not uniform, right, in the whole world.
It's not uniform at all. So here, actually, I also use just the electric field. So if you have the charge distribution, right? Use Poisson equation convert to like electric field spatial distribution. So what I have will have a very different electric field spatial distribution. It's not uniform at all. It's like a steeper decay. So if you use typical other ionic liquids, you might have a longer tail, but I will have a steeper tail. So also the electric field is different among the two ionic liquids. I also did not use any chemical reactions at the interfaces. So the entire difference in energy storage performance is due to the electric field effect.
Okay, so in that case, I saw some polarization, right? So how you control, okay, for example, the interface by using your ion liquid, okay, it's or is for example the positive and negative. It's just using some another electric field to separate the polarization.
So we put everything on electrode. So for example, AFM measurements with the rupture force location, we measure at very positive potential, measure at very low negative potential. So we measure a different location. So sometimes we squeeze cations into the first layer adjacent to the electrode. Sometimes we squeeze cations into the first layer. So they are different because if you squeeze the cation is like a smaller one, it's just beaming. But the anion is a larger one, so it's very interesting. Actually, it's asymmetric. I didn't show the complete set of data, but if you found a curve, actually it's asymmetric. So we measured the capacitance at different polarization degree. So it's very asymmetric. That is exactly due to the difference in structure between the cation and the anion. Yeah, we study all of them by either simulation. So all of our simulation are done on electrode as well. We'll apply different potentials on the electrode surface and let the molecules equilibrate and study the electric field distribution. Yeah. And I have.
Thank you. Yeah, I learned a lot. Okay.
Thank you so much.
Yeah.
Yes, Stefan. You can unmute.
Okay. Sorry for another question. Maybe a completely different area. Your amphiphilic layers are somehow similar to a biomembrane.
Yeah, right.
Yeah.
It's very similar.
Okay. Is there any plans to utilize that in different sense so biomembranes have special active channels for the transport of ions through these membranes? Is it possible to build something like that as well? So you use your capacitor more to build the membrane and also then somehow to equip it with such active channels for ion transfer. Maybe not at all for energy storage purposes, just to.
Yeah, I think that's a cool idea. If you were somehow be able to engineer the bilayer structure, for example, I know like the biomembrane have like ion pump, right? You have like a little pump to transport ions, and sometimes it's highly selective as well. So that's a cool idea, but I need to think about how to incorporate something into the ionic liquid. So yeah, if you can engineer the ionic liquid bilayer structure by incorporating some other species. So the ion pump are essentially proteins, like a multi-compartment protein, right? They have like little thing, like little interaction with anion and with like different ionic species. So if we do something like this, it might improve the transport properties across the membrane. It might somehow affect the electrochemical properties as well. But I don't have an ideas yet, like how to utilize that. But it's really similar to biomembrane. Essentially, it's the same thing. It's a self-assembly of the due to the interaction of the hydrophobic tail. So like the membrane, like the biomembrane is the same. You have like hydrophilic, hydrophobic, and you interact with each other, form bilayers. So yeah, that's gonna be a cool idea if we're somehow combining electrochemistry with bio experiments design.
Okay, maybe we can chat about that.
Separately. We can chat further about this. Yeah. So ionic liquids has been widely used for many applications, and not like spintronics, and also some other. I think separation processes as well. Yeah.
Okay, is there any other questions from the audience? Okay, you can just raise your hand or just type it in the chat. I don't see anything on the chat yet. Let's do. Okay, I see another hand raised. Okay, 1 second. Ben, okay.
Hi, Simon.
Hi, Ben.
Hi, nice talk. Really interesting. So I work a bit on sort of more, polymers with ion liquid, so mostly ionogels type of materials. What any special sample preparation required if we were to try to image, these ionic liquids within that polymer structure? Like, how do you process this kind of materials for imaging?
So I never image ionic liquids.
Okay.
So the only structuring technique we use is AFM measurements. So we don't measure something as a function of spatial 2D spatial location. Essentially, we have an entire film sitting on a flat surface and then using AFM tip to push through the liquid, but we don't go around to do the imaging. So that actually requires the table to be highly stable. So AFM, typically, if you just obtain the structural information of the flat surface, you don't need to have like a very stable table. But in order to perform the AFM force measurements, you need to have a super stable table and some special tip. So it's like force spectroscopy. So we don't typically move the tip around, we just push through. And it's like as a function of distance away from the substrate, not different locations. But I don't do any kind of like later part, like functional imaging on ionic liquid. Yeah, but I can.
Okay, yeah, happy to chat. Thanks.
Yeah, thank you.
All right, is there any other questions? Okay, well, let's wait for 2 more minutes. I'll ask a very quick question about your compete. Okay, as you know, you talk about your time resolution is not very quick. So are we seeing a sort of an average result across that time span? That if you have your fluorescence molecules and your topic molecules, once the fluorescent molecules left the surface, do they have the chance to come back?
Yes, so they don't have a chance to come back. And in my measurements, we need to optimize the condition to avoid the time averaging effect. So it's a very important question. It's a very important consideration when you design the experiments. So when I say it's broadly applicable, but it actually needs a lot of optimization. So essentially to test first, the auxiliary, the proxy reaction, does it change over time? And in our system, we use a flow cell. So essentially it absorbs, reacts, desorbs, and goes away. So it doesn't come back. But that's one thing to consider. Another thing is like, does the catalyst particle maintain its stability over time, right? So if the auxiliary fluorogenic reaction decays over time, it might create artifacts. It's not due to the competition. It's due to just the surface restructuring or decomposition of the catalyst particle, right? So we need to do, under our condition, a control experiment that the auxiliary fluorogenic reaction doesn't change its behavior over time. The catalyst particle is the same. It's very easy to do. So if we do compete image a different concentration, we need to have, for example, like 2 hours. We just need to do, okay, without a competitor, we observe the catalytic activities over time. It doesn't change the binding behavior, the frequency, so it doesn't change at all. So within that time window, it's stable. So that means our compete strategy is valid. But you're right, if we try to do a different condition, a different reaction, we need to optimize the whole system again. So what condition and what kind of auxiliary reaction we need to choose. So it's not super easy. It's the concept is widely applicable, but in terms of implementation experimentally, it takes a lot of efforts to choose and to do all kinds of control experiments. You have a very valid point. Yeah.
Okay, thanks for praising my question. Any other questions from the audience? I think it's already past 11. We have 1 hour planned for this event, right? Okay, then if there was no more questions, let's thank Xianwen again. Thanks for the nice presentation and very patient answering for our questions. I think we're going to have a few department seminars coming up soon, so please stay tuned for the news. Thank you, Xianwen.
Thank you so much, Chen, for hosting the seminar. And thank you everyone for attending the seminar. Bye.